Okay, thank you for the setting up this workshop and giving us all a chance to talk about stuff. Sorry for the mouthful of a title, but what I really wanted to do was talk about. We were fortunate to get the review gods smiled upon us, so we have a bunch of papers from our lab in the space of perception and autonomy for self-driving vehicles. So my goal in the 30 minutes was to really just give an advertisement for a bunch of posters and talks. And hopefully, if you guys are interested, you can go off and dig more into detail. Okay. So roughly the three kinds of topics that I'll talk about is, I won't really talk about end-to-end end-to-end autonomy. But instead, I'll spend the first, let's say, 10 minutes talking about building world models, in particular 4D world models, something that we've been kind of pursuing for a while. And one piece of work that we're pretty excited about is trying to build a 4D world model at scale. So Hytham will present this, or we'll give a poster on this on Wednesday afternoon. And essentially, what this is, it's a NeRF of Pittsburgh, built from, I think, the largest available sort of data set. I'm sorry, this is not available, this is private, but it's essentially built from a self-driving data set of millions of frames collected over a year spanning thousands of videos. And importantly, the things you wrestle with here are we want to reconstruct the rigid environment, which is essentially a map. You want to also have to deal with the movers in the scene. And I'll try to show you essentially some efforts of trying to build neural models that can synthesize how not just the static world looks, but how it moves. And I think one of the secret sauces that we've been pushing on to try to do this sort of dynamic 4D world reconstruction is, I'm assuming everyone in here has kind of seen NeRF-like models before, but the thing we've really been emphasizing is trying to not just reconstruct image pixels in terms of RGB reconstruction error, but really trying to understand motion. So you could imagine, given a whole bunch of these logs collected at scale, you extract pixel intensities, which is straightforward. You also extract motion vectors of how pixels move over time. And then we also throw into a mix self-supervised features. So I've heard the term used before when you have losses that suggest you want to learn 3D representations, or in our case, 4D representations that then project to the image pixels. We call that a photometric loss. When that projects to motion vectors, we call that a geometric loss. And when that projects to self-supervised features, other folks have suggested calling that a feature metric loss. So you can put this all into a big mix, try to learn a model that takes as input not just spatial position, but time. And in this case, we also had to deal with timestamps over different resolutions. One of the tricky parts here is that sometimes, clearly a part of the world is very static. We want to lean into that. There's other parts of the world that are very dynamic, people walking down the street. And there's also parts of the world that are what are called transient, like parked cars. And when you're trying to learn 3D or 4D models at this scale, you have to tease apart all these three. So we can look into sort of detailed models for how to do that. And then finally, one of the tricks for really learning at this scale was kind of revisiting old techniques from graphics. So this is from Thomas Funkhauser's thesis in 1990, where this was, pre-heavy-duty GPU days. Folks also built walk-throughable renderings at scale for large-scale buildings. And one of the crucial tricks of making that work was really employing visibility reasoning. And it turns out you can apply these same kinds of techniques of partitioning the world into cells and seeing what data is visible from what cell as a way of constructing data parallelism. So you can end up essentially building little NeRF models for different parts of the world, and you can allocate the pixels and rays that are useful for training that NeRF model for a particular neighborhood. So I think it's kind of fun to revisit some of these old graphics techniques for learning models for efficient rendering at scale, and I think they can be useful for doing things with this kind of urban scale NeRF 4D modeling. And another thing that I think is kind of fun, and maybe if you come from the self-driving world, this is obvious, but I think if you come from the NeRF sort of view synthesis world, this might not be. Because usually view synthesis is thought of as a technique for creating pretty pictures. in the self-driving world, actually, there's a very important use case for this called resimulation, which is you collect original data, which is shown in the top. Unfortunately, this is a re-rendering, not the original pixels. But what's incredibly useful if you want to really build a kind of 4D simulator is being able to say, well, what would the world have looked like if I had moved differently, if I had moved over to the left lane, if I had slowed down? And essentially, this is a view synthesis problem. So I think this is a beautiful, use case for NeRF models, except that, of course, the crucial thing here is the world is dynamic. If it was just a static thing, it's not so interesting to model because we want to sort of understand how to move in this dynamic world. So you can do things like, simulate what the world would look like if I'd moved to the left. You can even do what I think is neat is not just extrinsic view synthesis, but intrinsic view synthesis. So you can imagine that I have the same location of a camera, but I swap out my sensors, a near field fisheye lens for a normal lens. And all of this kind of just falls out of the NeRF framework, which I think is a pretty kind of effective way of looking at this kind of data. And I think one of the things that to me is super attractive about really embracing this 4D view is that now, if you could really build 4D models that understand 3D structure and also how that 3D structure changes over time, you should be able to use those models to forecast, to predict how the world will unfold in the future. So essentially forecasting 4D models. And I think this is, I think, very evocative of things that we certainly see in language, of trying to build models that predict the next word given previous words. And I think there's a very compelling argument to be made of you could try to predict the next 3D point cloud given the previous set of 3D point clouds. And I think one of the sneaky wins in trying to phrase it in this way is for language, a very practical aspect that facilitates large-scale learning is that words are so compressed, and you can actually store an enormous data set of text, trillions of examples, in a somewhat feasible way, which is still very difficult to do for images. But I think point clouds live somewhere in the middle. I think we can learn at scale with point clouds. So something we've been looking at is to trying to build these 4D models, but learning them at scale exclusively on point cloud data. So you can imagine a very simple way of doing this is if you follow this view of like next word prediction, in this case, it'd be next LiDAR frame prediction. Given the previous set of T LiDAR frames, learn a network that predicts the next T set of LiDAR frames. And you can compare that to the ground truth because that's what you observe and you backprop this loss. But here's a case where just doing the naive kind of machine learning solution, I think there's a place to put envision smarts into this. And that is so much of what we see here, the change in what we see is not due to the dynamics of the 4D world, it's due to the changes of the sensor. And this is kind of obvious when you think about it. You can imagine having a rigid world where nothing is changing. The only thing that's changing is the viewpoint of the sensor. But if you look at the sensor readings, the 3D points that you get out, they will appear to change. But very clearly, the world is not changing. It can be static. And this is kind of obvious when you think about this. Well, it's because the world is rigid, and what these points, they don't represent actual physical things on the corner of surfaces that you track. They just represent intersections of rays from a sensor with the 3D geometry. So in some sense, we really want to tease apart the modeling of the world versus the modeling of the data. And a very simple way of doing that is we NeRFify this. So we replace this feed-forward model with something that, instead of predicting points, it actually predicts occupancy, 4D occupancy. And you can represent this with an implicit NeRF or some explicit voxel triplane representation. But given this, we can now render it from future positions that we know in the data. And now we can compare this rendered model to the actual future sensor data that we see and use this as a loss. And now what's cool is the model internally will learn this, this representation of the 4D world as it evolves. And when you do this, it ends up being considerably more accurate than previous approaches, because previous approaches tend to directly model the sensor data versus what we're doing is actually, I think, modeling the world underneath. And one of the fun aspects of this is because we're modeling the world underneath, we can re-render it from different sensor intrinsics. So you can re-render it from a 32 beam LiDAR or a 64 beam LiDAR. And there's a statement here I'd like to evoke. I remember meeting Judea Pearl at at a PI talk on a grant, and he made this statement that always stuck with me. He said, "We should be modeling the world, not the data." And I think from his perspective, he was really pushing causality as a first-class citizen. But here's an example of the world is really 4D. It's not points. The sensors are points. So if you make a commitment to modeling the world, you get all of this, I guess, sort of kind of generality, I think. Okay. Behind my time here. And in the space of 4D modeling, something else we've become very interested in is really trying to model 4D scenes. So we have a slew of work that really focuses on much more dynamic scenes, not in the outdoor setting, but I want to highlight it here because there's a bunch of folks in the lab who've been pushing toward a very large scale code release, which is out this week. And I want to just advertise it for folks that might want to use this. And I'll show some examples on using it on outdoor scenes. But essentially, this idea of trying to model dynamic scenes, we've quite a bit of work on, and Genshin can tell you more about it in his poster on Thursday morning. But one of the sort of take-home messages here is that applying the same kinds of technique that I talked about for modeling the 4D Pittsburgh world, if you do it in a scene of a video collected from an indoor setting, you can still very tailored views, but we actually build 4D reconstructions of the world. And if we can, we should be able to, in this case, we end up using depth sensors as well. So with a lot of sensor rigs and self-driving, we have LiDAR data as well. And if you have that, I'm just going to sort of show off some results of you can get reconstructions of the world, of the dynamic objects. And now, because we're reconstructing dynamic objects, we can re-render it from arbitrary viewpoints, including virtual viewpoints on the dynamic object. So we'll show a re-rendering of a cat moving around from the cat's point of view, and also from a little camera that's following the cat right behind. So these are the kinds of things you can do if you have a 4D world. This one's kind of nice. This is what the world looks like from the cat's perspective. And some more fun examples. Okay. And so we're essentially preparing a code release for what we call like 4D world modeling using NeRFs. And it should be out this week. So the students have put a lot of effort into making this sort of a user-friendly code base and examples of both indoor and outdoor scenes that are importantly dynamic. So that's the sort of point of emphasis here. Okay, all right. So that was really, let's say, the bulk of the talk on sort of 4D multimodal understanding. I want to keep an eye on the time here. I think I have 10 more minutes. Just want to see here, 10:30, 10:35. Okay. All right. So for efficient perception, so I'll just sort of throw this off as another a kind of natural extension. A lot of these techniques that I talked about for building these kinds of 4D models are pretty compute intensive, because essentially it's solving this, it's trying to address vision with this analysis by synthesis view of differentially optimizing an interpretation of the world to match what you see. So this is relatively expensive. It takes hours to do. And so these kinds of models learned from here won't work in an embodied robotic setting. Because we have to respond in milliseconds before we get the next sensor frame. And so we were wrestling with this predicament that we can do this very expensive, like 4D graphic style optimization to try to understand how the world is moving around. But at the end of the day, for robotic applications, we really want fast feed-forward models. So how do we reconcile the two? This is kind of a trivial observation, but one is we just distill a feed-forward model from this huge collections of offline models that were trained expensively on large collections of video repositories. So essentially, we've had lots of discussion on, or I assume we will have discussions on sort of foundation models and what they could mean and implications for self-driving. My own personal view, I think what's kind of needed is something like a 4D foundational model, where this is one of the lessons I took away from my time in sort of the self-driving world, that historically, I sort of tended to focus a lot more on recognition problems, but once you're in that space, it becomes really clear that the high order bit is understanding what is in front of you, what's the empty space, and how that's moving and changing, as opposed to labeling things. So I think building this 4D understanding, it seems like we have tools that can do this with a very expensive approach that involves differential optimization. But essentially, we can still do this at scale on sort of, let's say, internet scale video footage, and then try to learn models from there that can be distilled into very fast, efficient feed-forward architectures. We have an example of this that Jeff will talk about on Tuesday afternoon. Okay, I'll skip this in the interest of time. Everyone wants to hear about sort of efficiency and saliency. Something that I've always been intrigued at is if you really want to make things fast, one of the first things everyone does in a robotic setup is you take all your sensor readings and you throw them away. You start subsampling frames, you start subsampling pixels. It always breaks my heart because you spend all this time creating this very elaborate sensor rig and you throw away a decent chunk of it because it's too expensive to compute on. But humans don't do this. Humans saccade and foveate. So we have a paper that sort of gives an example of trying to do this kind of trick that's GPU friendly that Chitesh will talk about Tuesday afternoon. Okay. And it turns out by doing these kind of sort of attentional reasoning, you can do much better on finding small objects, which I think is going to be important for at-speed navigation. So, for example, autonomous trucks. Okay. And so now in the last few minutes, I want to throw out just a few, kind of get a discussion going on multimodal foundation models and what they might mean for self-driving. And I want to motivate that by this problem of open world perception. So one of the things that I found curious, I've been interested for a long time, is kind of long-tailed recognition. And what you find is if you look at a lot of these sort of perception data sets for self-driving, they'll annotate a huge number of objects that are relevant, you know, strollers and people and kids. But what happens is during evaluation, they ignore a whole bunch of the rare ones because there's not enough of them. At some level, this has to be the wrong way of framing the problem. So if you take a state-of-the-art object detector, apologies, Philip, are you here? If you take a state-of-the-art object detector, then actually try to train this on these rare classes, you kind of get shockingly abysmal performance. So this to me is almost clickbaity. So you try to train a stroller detector, you try to train a child detector, and it gets less than 1% performance AP compared to these common classes. And it turns out if you do a bunch of fixes, you can improve this by a significant amount to 20 or 30, but that's still well short of what you would like to have. And I argue what we've done in the self-driving world is that we sort of have a semantic blind spot. We focus so much on cars. And in fact, a huge number of papers and work in the space of 3D detection focus exclusively on single objects. And so we kind of forget that there's all these other objects out there. And in some sense, this seems clearly that it feels like this is the wrong way of framing the problem. We can't just ignore children because they don't happen to appear a lot in our self-driving data sets. And I think one possible solution here is really bringing to bear massive pre-training data, perhaps in the form of foundation model. So you can go right now, type into DALL-E, a stroller with 3 wheels in the winter pushed by a man, which is very hard to find images of, and it will generate images for you. So somehow it seems like this notion of trying to deal with things in the tail, things that we have typically low examples of, we should really leverage these massive data sources that are now available to us. And so this is more of just starting the conversation. I don't really have an answer here, but we have one attempt at trying to look at this. And that is really leaning into this notion of these massive data sources. When they're multimodal, they kind of let you do some interesting things. One is if you want to. So one claim is that I think I'm willing to stand behind, that in the future, we really won't train anything from scratch. We'll always download a foundation model and then adapt it to our task of interest. So then it feels like a really crucial question is exactly how do you fine tune a foundation model? Is it just fine tuning the way that we normally do it, or do we have to do something special? And I think in the context of when you have multimodal models, you can actually do something kind of interesting where you actually fine tune on multimodal data. So what I mean by this is there's an example of if you have visual examples and you have textual examples, a really almost trivial trick for fine tuning is you encode both of these in your normal text encoder representation, your vision encoder representation. These produce features that are all the same dimensionality and are trained to live in the same space. And just think about this as now, instead of having 2 examples, you have 3 examples. So you just get this sneakily additional data and you just train your normal classifiers on top of it. It turns out this happens to be a very effective and sort of state-of-the-art way of fine-tuning or linearly probing foundation models. And it has this sort of nice flavor that if you actually want to try to recognize things, you can actually learn representations that are truly multimodal. And we have this fun example of basically by looking at text of dogs, you can build better visual classifiers for dogs. And by listening to dogs bark, you can build better visual classifiers for dogs because you still learn this multimodal representation space. So I urge you guys to sort of take a look at that. All right, and so maybe if I have one more minute, I'll give another fun example of this kind of multimodal cross-modal recognition. That is looking at this problem of, I'll show you like this, looking at this problem of given images trying to produce street maps. And this is something that maybe in the vision community we haven't looked at a lot, but this is clearly a huge component of at least a lot of approaches to self-driving. We build maps that tell us what we expect to see in the world. And it's such a powerful prior because even when you have your eyes closed, you can still sort of make guesses about what you expect to see, where the stoplights will be, where the lane geometry will turn. But a very important question is how do you build these maps automatically and how do you keep them up to date? Because if these maps become stale, you can actually close your eyes and think the wrong thing, and you get you can get very disastrous consequences if you don't if you can't trust what you expect to see. And so there's a question of there's a problem that other folks have suggested of can we give an imagery spit out maps, where maps are this kind of computational graph structure of nodes and lane geometries with edges that connect them. And we just sort of explored a really simple approach based on cross-modal nearest neighbors. So essentially, you can build representations for graphs and build representations for images, and then try to learn through contrastive learning, representations that allow you to match the correct ones and not match incorrect ones. And by doing this now, given an image, we can just retrieve the closest matching graph with the closest similar embedding. So you can essentially think about this as nearest neighbors, but you're doing this across different modality spaces. And what we find is that this actually works very well compared to other more classic vision approaches that try to explicitly find pixels and link lane geometry in the image space. So I don't know if this is the final answer, but what's kind of fun about some of these examples is that this idea of cross-modal retrieval in some ways is even more flexible than typical sort of unimodal nearest neighbor retrieval, because which by itself also works really well, almost comparatively to the state of the art. Here's a sham for loss. So the idea is that normally if you want to try to apply, let's say, nearest neighbors to the problem of spitting out row geometry given an image, you have to have a bunch of stored examples of images and row geometry. But what's cool about this is you can just have, all you need is a stored library of row geometries that don't need to be paired with image geometries. So what that allows us to do is even create augmented graph libraries by just augmenting graphs, because that's all you're matching to. So you don't need this paired data, and that by itself gives you a huge win. And maybe sort of more fun examples of cross-modal stuff in the generative space, moving from sketches to images. I'll skip that for the time being, but maybe I'll try to kind of summarize the high-level points here. So in terms of sort of 4D understanding, I'm sort of convinced that this is the crucial problem to really solve. Even if you really want to build end-to-end models, I think in order to train them, it seems like training on real data is going to be super difficult. And this idea of if we can actually take real data and build little 4D simulators of it, that seems like a powerful enabler to try to then do more end-to-end learning. And what we find is that for this 4D understanding task, the real crucial bit is understanding pixel movement. I guess there's this more kind of meaningful thing. If you do that, all of these things are very expensive. How can you actually distill them into fast things that can operate online on a robotic platform? We can do things like distillation. I guess that's not too hard, I think. And finally, these open questions that I think we're just starting to explore is how do you really bring to bear these large scale models that might have been trained on much more data, and also kind of interestingly across different modalities, which I think is super interesting and relevant for perception in this setting. All right, so with that, I will end. Let's see if there's any questions.
Any questions from audience?
Sure, thanks.
Wonderful talk as usual, Deva. Every time I hear you speak, it's like a year's worth of good ideas. I was very interested in the thing about the stroller and the fact that the rare classes are so bad. And it's a little bit weird to me to say that, well, you know, this stroller thing never appears and it's hard to find it in the data, but if you go to DALI, it's there, right? So probably the answer is that there's tons of strollers in Lion, but probably most of them are driven by women, and maybe like other things are different. But doesn't this mean that somehow if you just have some sort of self-supervised pre-training of your model, you don't need to go for text. You can, the data is still sitting there. Like there are strollers. All you need to do is just get them out without the label, right? It's the label problem, it seems. It's the text problem, not the pixel problem. The pixels are there.
Yeah, okay. Seems to be a bit more compositional. So I can say, and Dolly will do this, a car with 2 front doors open and the trunk open and someone getting in. And that just seems super hard to observe. Right. And so this question of how compositional is it really is I guess up for debate, but yeah, you're sort of pushing against it. Do you really need language in this story?
Right. Compositional should be in the pixels as well, but you're saying, I guess, it's harder to get at it.
Yeah. So for example, another interesting problem that comes from this kind of like virtual world stuff is that it's also super important to, it's a bit more mundane from the vision perspective, but like validate these models. So you have something, someone gives you a model, you want to know, when does it fail? Like, is it going to work when there's a stroller that has 3 wheels as opposed to 2? And then there's this weird question where I feel like I think some sort of language might help, because it lets you to sort of understand the ways you want to push and poke at this, instead of just being purely data driven. But fair question. Exactly how much language is going to play into it, I think is a super interesting question.
Thank you.
So another question from the audience. Yeah.
Yeah, first, thank you very much for the talk. I've learned a lot. And my question is also regarding this, the stroller kind of example and the whole framework of using kind of foundational models to create all of these long tail examples. And is there a concern regarding the distribution shift from this kind of data set that is, generated using generative AI versus what the autonomous vehicle would see in the real world, and how can that be addressed and validated?
Yeah. So at least my own personal view is that at some level the distribution shift is okay, because like the real world is so skewed. Like the natural distribution is that I don't know the last time I saw a 3-wheeled stroller pushed by a man. So in my natural distribution, it's almost never been seen. So I think at some level we need some artificial shift at the very least for probing and analyzing things, for validating, and then maybe for training too. But handling that shift, I think, yeah. So I guess at some level, I think we need a shift. It has to be part of the story. But then given that it has to be part of the story, like, does it mess things up or not? My initial thinking is that it's not so bad. Like sometimes we intentionally rebalance to deal, like that's almost one solution for long tail learning is, we oversample the rare stuff or we undersample the common stuff. So I guess I'm not as worried about the distribution shift due to like placing objects. Maybe it's more about like learning faithful models of like how to place them. To me, that's a little bit more related to this world modeling, like understanding where are objects typically, how do they move. If we do that, then hopefully we can take a synthetic thing of a three-wheeled stroller and actually put it in a reasonable place and have that be faithful.
Thank you very much.
Yeah.
So maybe we have time for the one last question.
Thank you so much for the impressive talk. Yeah, we are very interested in the 4D understanding, and we find that if we go that to the NeRF way, it's very like dependent on the quality of the capturing data. For example, the coverage of frames over the scene. And from your experience, it's like nowadays, is there any public data set can already satisfy all the need, or you really need some like industrial level, like the recordings and data set to satisfy this for the understanding?
Yeah. So I guess there's 2 points to bring up is that. So I think one big difference between like NeRF and the way that's typically done, and then I guess what we're thinking about for this application is that we don't get crazy amounts of views, in the sense that we have a limited, like normally NeRFs you have, I don't know, 100 viewpoints, scattered around an object, and so that's not the case here. You have very associated viewpoints because it's essentially one stream of sensor movement. So I think it's a kind of different NeRF problem, but I think it's super interesting. So how do you learn when you really don't have that much multi-view data? It's really the views are not as spread out. And then in my own thought there was that, I guess the question you're really asking is that, do we need other data sets to really explore that? And yeah, I think I would agree. Like to really push this, one of the things that I would like to be able to do is that, can we build models that really tell us how the 4D world behaves, what objects tend to be there and how they tend to move. And that kind of scale of learning, it seems like it's not publicly available, certainly not in terms of LiDAR data. There's a hypothesis that maybe in terms of video data, it's there. But the thing that I see is that, the reason why everyone is trying to do video-based foundation models, and I think the reason why it's really hard to pull off is because if text was hard to manage, then images are way worse, and video is just way, way worse than that. So I think it's not even just a data problem. I think it's like a compute infra problem. But even if we had the data,
in your view, in the future we'll get there, right?
Yeah, I think so. I guess I'm sort of optimistic, but yeah, we'll have to kind of solve, I think, a bunch of almost like systems level issues, like how do you manage stuff and compute at this kind of scale?
Okay, thank you so much.
Yeah.
Okay, so let's say that again. So we have a slogan for you.
Oh, cool. Thank you.